All right. So today we're gonna continue our discussion on non-local operators and super selection sectors. I'll have to go on the board a lot today because I'll try to explain things a little bit better. All right. So what we discussed last time, if there are questions as we go along, please do ask. In the previous lecture, we talked about we started by saying that in QFT1, we said stable particles are irreducible representations of the Poincare group, labeled by whatever we label EREPs with. In the case of Poincare group, spin and mass. Sorry. Whoops. Spin and mass. Right? Okay. But when we have global charge, when we have charges, we end up with reducible representations and super selection sectors. The most important thing that I want you guys to keep in mind is the following. When you have global charges, there is absolutely no meaning to superposing states with different number of charges. You could superpose two different states with a single charge, as we were just discussing, but you cannot superpose vacuum with a state with a single charge. That is equivalent to a density matrix. You could put them in like you put them in classical probabilistic distribution, and that's what we mean by saying that there are super selection sectors. All right, so there are various aspects of this. There's a whole theory of super selection sectors, and I want you guys to have this picture in mind. So the charge neutral operators versus charge fields, right, is one aspect of it. There's additivity versus Hog's duality, and then R-form symmetries.
So with gauge charges, I guess the idea is you don't have a conservation loss, so you're allowed to mix between two different standards.
No, we're going to discuss. You don't know anything about gauge theory yet. So far, this was the previous lecture was about. Previous lecture was about global symmetry, right? And as we said, there are super selection sectors. Today, I'll describe everything for R-form symmetries. Good. Okay. So, review of what we discussed last time. We talked about causal complete regions, right? So there's a notion of a causal complement associated to a region in space-time, and a causal complete region is equal to its double causal completion. Why does this matter? Because of causality, right? So we went over that. In quantum field theory, what we do is to regions of space-time, we associate subalgebras of the bounded operators of Hilbert space. There's a single Hilbert space, right? Infinite-dimensional, countable Hilbert space. Nobody should ever talk about uncountable Hilbert spaces, even if you're in QED. Okay? Causal complement goes to commutant. That's desirable. Commutant is a set of operators in B of H that commute with your subalgebra. So a causally complete region is equal to its double causal complement, goes to a von Neumann algebra. All you need to know about a von Neumann algebra is a subalgebra of the set of operators on Hilbert space that is its own double commutant. That's a very definition. That's a definition of von Neumann algebra. So a net of causally complete region goes to a net of von Neumann algebras. That's just formal. But this, for now, what I want you guys to think about is we're going to talk about causal developments of a ball or half spaces. I'll try to keep everything above ball-shaped regions. There's a long story of like half spaces as well. It's even simpler, but because I want to stick to local physics. All right. So what is locality? Locality are the following axioms. Inclusion goes to inclusion. This is called nesting. If there's a region, let's just, for the rest of the talk, we're going to be talking, sometimes I draw space-time diagrams, but imagine I can talk about ball-shaped regions like this, right? So nesting means the following. If A is inside B, B is the bigger one, the algebra associated to A is the subalgebra of B. Covariance. It says that if there is a transformation that sends A to a tilde, for example, translation, which leaves everything else invariant. For example, this is a killing vector, isometry. The metric doesn't change, right? It's isometric and sinusoidal transformation. Then it must be realized as a symmetry of the in the Hilbert space, meaning the vacuums. There has to exist a unitary in the Hilbert space that does realize this. It has to be represented that way, and that unitary is gonna kill this guy. Well, it's gonna leave it invariant. Sorry, it's a statement that the vacuum is invariant.
Now can you also propose these two charts? You have a charge here based on the symmetry. Then now can you do the superposition that we were talking about those? We can superpose two states with the same charge.
Yeah, sure, yes. For a single, yeah. Are you talking global charges?
Yes.
We'll talk about that. Well, I'll actually talk about that in a bit. But for now, all we care about, like the idea of associating algebras to regions, at the core of it is is locality, right? Right? Because as we saw last time, if there's a region which has two disjoint parts, A1 and A2, if you associate an algebra here and algebra here, you would want the algebra of the two to be the additive algebra, putting the two together, unless you have non-local operators. So we would like to genuine non-local operators. We want to rule those out. How do we try to rule those out? Duality. Duality is the statement that the algebra of the causal complement is the same as the algebra, the commutant of the algebra. This has been proven for topologically trivial regions in quantum field theory, but for topologically non-trivial regions is going to be the sort of charges. Now, if a theory satisfies Haug's duality for arbitrary regions, we call that theory complete. Meaning what? It's equivalent to saying that it has no R-form symmetries. No symmetries of any kind. Generalized symmetries. Here's something I said casually last time, but today we're going to discuss it. I said the algebra of a topologically trivial region satisfies Haug's duality. So how do I talk about non-topologically trivial regions? We're going to talk about the homotopy class. So homotopy class, phi 1, phi, 2 pi d. Well, actually d minus 1, space-time, right? If you pick a region that has non-trivial, we'll see that today, pi of r, and its algebra is not additive, it has brand new operators, we say the theory has R-form symmetry. And that's when Haug's duality fails for these regions. Right? Good. So now you see I drew this triangle, R symmetry, Haug's duality, additive versus dual algebras. Right? Okay, so we're going to go over this today. Now, last time what we talked about are regions with non-trivial pi 0. So if you don't know topology, what pi 0 is the number of disjoint regions. So if this is a space diagram, this has two disjoint pieces, right? So this has non-trivial pi 0. Good. So consider the following transformation, rotation by 2 pi. Okay? If you have a local operator, depending on spin, under rotation by 2 pi, it will pick up this phase. If it's spin integer, it will be unchanged. If it's spin half integer, it will pick up a minus sign. Example of such an operator is a fermion. Of course, a single fermion cannot be observable. But a single fermion need not be attached to a Wilson line, right? That is the case if you have a gauge theory. But a single fermion on its own right could exist, and you have still a global charge. Well, sorry, it's unphysical. You have to have pairs of them, right? Those are the observable. So charge neutral observables are the physical ones. Now, there is a sense in which to talk about a universe with no fermions, the state with no fermions, state of the universe with no fermions that's invariant under this transformation. And then there's a state of the universe with a single fermion that under this transformation picks up a minus sign. The vector picks up a minus sign, right? The expectation values are invariant. Now, if it was sensible to superpose vacuum with the state psi, the issue that comes up is that when you look at the expectation values in such states, there will be off-diagonal terms, and then you'll pick this minus sign will become visible. That is why we have superselection sectors. We went over this last time. Good? I said that a second ago. There's no meaning associated to alpha of vacuum plus beta of a single psi except for this. We have superselection sectors. All right. So now I want to define what a global charge is as what we're going to call the DHR charges. This is synonymous to global charge. This is more rigorous terminology for global charge. First, it said purely local excitation, meaning that you could do it, if you introduce a charge, global charge, if you put a fermion here, spinner here, a guy who is like really, really far away, space like separated, would have no way of knowing, right? So they're local in that sense. And then they are transportable. That was a question that was asked earlier. If I apply the transformation, some symmetry of the vacuum, this will be transported. I'm not going to define it rigorously, but it's transportable. A transportable local excitation is what's called the DHR charge, otherwise known as global charge. Good? A gauge, an electron is not a DHR charge. Why? Because this guy out there will measure the Coulomb. Using Coulomb law, we'll measure the electric field, and we'll know there's a charge there, right? That's why electromagnetism is not a global charge theory, it's a gauge theory. Okay? Yeah.
When are things not transportable, or are things not transportable?
Let's not get there. Just honest answer to questions that I don't know.
That's the thing I didn't get. So suppose I'm able to fit.
I'll go over that. This is just in words, we're gonna go over it. All right. This is my review still. But from the review, I'm trying to motivate it. But if I don't answer your question, I'll see you again. All right, so this is an example we went over last time. Take the constant time slice and two regions. This region has two disjoint parts. It has non-trivial pi 0. The additive algebra of charge neutral operators does not include this particular non-local excitation. A charge q here minus q here. Notice that what's important is that in the theory of global symmetry, this excitation, these two guys are not attached by Wilson line or anything. These are just two excitations. I can put a fermion here and a fermion there. And if it's not a gauge theory, I don't need it to have a connection, right? Good? All right. So this, we gave it a name. We called it, well, by local charge operator or intertwiner. Every time they exist, it's a failure of duality. Oops. Why? Because the algebra of the causal complement, which is C, commutes with the IAB. This is in the commutant of this. But the commutant of AC is larger than the algebra of AB. They're not equal. Therefore, Hawk's duality for C has failed. Good. Hog's duality failing for AB means that there is an operator that commutes with the additive with the algebra of A and with the algebra of B. Whoops. Right? But it's not in the algebra of C. What is that? It's called the twist operator. That is -1 to the power of fermion number here. It's basically applying the group transformation here, right? That this is called twist, right? It's supported here. It commutes with A and B. Why is that? It's clear that it commutes with B, right? Why does it commute with A? Why does it commute with the algebra of A? Because the algebra of A is charge neutral operators. This is always even for those operators, right? Twist is dual of IAB of the intertwiner. So these guys come in pairs. This manifests the failure of duality for C. This manifests the failure of duality for AB. You cannot fix them by enlarging the algebras because these two guys don't commute. And that's generically the case. We'll see that.
Can you repeat that?
So the algebra of AB, you could try to enlarge it by including this intertwiner to make sure that Hog's duality for C holds, right? But then you see that the Hog's duality for AB fails. So you say, I'm going to enlarge the algebra of C by twist. But now this will mess up the previous one because these two guys don't commute. Once you include IAB in here, twist cannot be part of the other guy because they don't commute. There's no way of fixing it for both of them at the same time. So Hog's duality is just gone. Good? All right. So this is a summary we went over last time. I'm going to explain this a little bit more and then generalize. Yeah.
Sorry, really quick, like, is there like a strict definition for when two operators are dual, and in this sense, those operators are dual to each other? A bigger definition for dual operators?
No, the terminology of, so let's call Hog's, okay? The word duality is broadly used in physics, right? Let's use Hog's duality, right? But the content is clear, right?
Yeah.
It is related to duality, but I don't want to go there. There's a whole course that I'm not qualified to teach. Good? All right. So I said this before, global charges, what's special about them is that they could be localized in a finite ball without altering the physics outside of it. So a guy who is really, really far away in Andromeda Galaxy would not know that there was a pair creation. Pair creation is allowed because that conserves charge, right? Q minus Q created here. They would not know. It has to take, it takes something that propagates speed of with speed of light to get there for them to know. Good. However, this does not always hold. As you know from gauge theory and Coulomb law, this does not always hold.
That's the thing. If I'm able to create charge, electric charge, let's say.
You cannot, but yeah.
I mean, yeah, but suppose I'm able to manifest.
Yeah.
Then what you say is that that action is going to, the information about that particular charge is going to propagate infinitely fast.
There's no paradoxes because you cannot do that operation. Therefore, there's no violation of locality. So it could not create a charge spontaneously out of nowhere.
If I were
Everything
to
is
do
consistent.
so, then you would expect.
You would have violated locality.
Yeah.
Right. Okay. Now, what I'm going to do is, what we're going to discuss is a unified framework that puts global symmetry next to next to gauge theory, global charges next to gauge charges and generalized charges. Okay, so we're gonna describe all of them together. So in theories with global symmetry, we took a region with non-trivial pi 0, and we had these non-local observables. By non-local, hopefully by now you know, non-locally generated. Cannot be locally generated, sorry. In gauge theories, there is this operator, but this is the Wilson line operator. But this guy, so previously we said that this pair commutes with C, what's outside. But this doesn't commute with C because there's a Wilson line that goes through it. Here, there's no paradox. Right? Here, there's no issue. To see the issue, how do you diagnose the existence of Wilson lines or Wilson loops? You have to look at the region with non-trivial pi 1. What is such a region? Like an annulus in 2 plus 1 dimensions. Pi 1 is a fundamental group. It's the loops that wrap around this, right? So a Wilson loop that goes around this. Now, you could view this this annulus as as merging two topologically trivial regions. Each of these guys are topologically a disk. The gauge invariant operators of B and the gauge invariant operators of A cannot create this excitation. Right? So now there is a failure of additivity for regions with non-trivial pi 1. Good? Now here's a question. What about twist? What is the analog of twist? So it would mean that, so the existence of this guy, this Wilson loop commutes with the algebra of C. It's in the commutant of C, right? What is the analog of twist? All right. So the existence of this guy tells you that Hog's duality fails for C, right? Twist would become clear about the failure of Hog's duality for AB. What is that object? You probably don't know it yet, and the rest of the lecture is going to be about describing that in electromagnetic fields, E&M. It's called a 't Hooft operator, or in 4 dimensions, 3 plus 1 dimensions, it's called a 't Hooft loop. Sorry, this is poorly written. In 3 plus 1 dimensions, which is not this picture, this is 2 plus 1, right? In 3 plus 1 dimension, this is called the 't Hooft loop, so it's also a loop operator. I'm going to show it in a second. And in the case of in E&M, in 3 plus 1 dimensions, it's called a Dirac string. It's another non-local operator of E&M. Okay, good. The rest of the lecture is about telling you, well, actually, I'll first generalize, and then I will go over what the heck is a 't Hooft loop. All right? Questions? It's something very foundational, right? So by now you should see that there is something about electromagnetic field, Maxwell equations, that you might not have noticed. I already told you about these non-local operators, right? That are Wilson loops. There are other non-local operators. I have to explain them. What they do you know what they are actually? Anyone wants to take a guess? I already told you that I called it a loop. That means that in 3 plus 1 dimensions, it has it's associated to a loop. So it lives in a circle. You know why? Oh. All right, good. Okay. So let's draw pictures in 3 plus 1 dimensions. We need a region with non-trivial pi 1. Such a region, such a region in 3 plus 1 dimensions, so forget about plus 1, is a torus or donut, right? The non-trivial pi 1 of it has to do with the Wilson loop that runs here. Good. Now, this is a fact about topology. in flat space, if pi 1 of a region is non-trivial, the complementary region, the causal complement, will have non-trivial d minus 3 pi fundamental group, homotopy group. Okay? In 2 plus 1 dimensions, this is 1 as well. That's why it ends up being a loop. Good? Otherwise, it would be a hard dimensional operator that I'm not going to describe. So 2 plus 1 is nice because I can talk about it in terms of only loops, loop operators.
This is a theorem, right?
Huh? Yeah, it's just a fact about flat space. Yeah. So this is a Wilson loop. The operator, the dual, the analog of twist is a loop this way. That's called Tooth loop. But or a Dirac string for E&M, but it's not an integral of a mu. It's an integral of another one form. That's all defined. The dual vector field. So I'll have to describe duality. This is Hodge duality, by the way. It's another. Right, everyone's with me so far? If you have questions, ask. I'll try to explain what this is. For now, I'm drawing pictures and telling you where things are. But we're going to spend time describing this.
When you say, okay, you have non-trivial pi 1.
Yeah.
Then the only other non-trivial is pi d minus 3.
No, because remember the discussion I had before? I wanted to fix Hodge duality here. It was related to the causal complement. Once I have a region that has non-trivial pi 1, its causal complement has non-trivial pi d minus 3.
Okay. So it's our prime.
Here, R, I didn't tell you what it is. Right? Yes, but yes, here's the next statement, right? Yeah, correct. So when pi 1 of R is non-trivial, then pi d minus 1 minus 3 of R prime is non-trivial. But yeah. So thank you. I think maybe I should put prime just to avoid confusion. Thank you. Good. Any other questions? This is a very fundamental thing about electromagnetic field, E&M, that we do not teach at lower level physics class, but you have heard bits and pieces here and there about it. So it's about something, a statement about dual vector field. So a mu is, so I said that, next to local E and B, there's also integral, there's also, like e to the power of I integral of a mu dx mu. This is a non-local operator. There's another non-local operator, so it's called Wilson loop. And E&M is called a Dirac loop, which is this. A tilde, I'll explain to you what it is and how it's related. Good? This is called the dual vector field, the dual field, the dual for one form. That's a proper terminology. This is all easily explained on the lattice. This is what I taught a couple of years ago. The lattice story is very, very trivial. But here is maybe a little bit fancier. Good? Okay. So let's jump into it. Before jumping into it, I'm just going to show you one slide to think about what is generalized symmetry. A theory, we say, has R-form symmetry if regions with non-trivial pi R, the homotopy group R, have non-locally generated observables. When you have non-local pi R for a region, the causal complement will have non-trivial pi d minus 2 minus R. And the failure of duality with that is related to a dual non-local operator. Intertwiner versus twist. And everything you saw generalizes. But this is just for you to know. This is like research material that's being developed these days. Even though the mathematics of this was discovered a long time ago, but this is like really state-of-the-art. Papers on this kind of stuff is like past 5 years. Okay. Alrighty. Any questions? Now, the rest of the talk, as I promised, is going to be about what the hell is this A tilde? What is a Dirac string? These are non-local operators. To see this, let's go back to Maxwell equations. Here are the Maxwell equations, these four equations. There is some sort of an asymmetry that you probably noticed, that we put the divergence of E equal to 4 pi electric charge density, but we don't put a magnetic charge density. We don't assume a magnetic monopole, right? Nothing forbids a magnetic monopole. It could be there, all right? So if it is there, there will be some, it will carry some unit of charge, like G, the same way the electric charge was electric charge, right? This will carry a unit electric charge, and then the magnetic field will be outwards this way, given by G r hat over 4 pi squared. There will be an analogous magnetic Coulomb law. You just integrate around this and get G. You can probably see where the dual field is. Once you put a magnetic charge here, there is a new symmetry of E and M that becomes manifest. What is the symmetry? Roughly speaking, swapping electric and magnetic fields. More technically, you send electric field to B and B to minus E. That has a name. Do you know what it is? Anyway, we'll by the end of the course, we'll get there. All right? You're on the right track. You're on the right track. Good, everybody's with me? So you put rho M here, and you have to put JM here as well. Once you have rho M, you will have to put it covariantly. So this is JM. Because rho E and JE sit in a vector multiply, right? Vector, they transform as a Lorentz vector, right? Here is the corresponding Lorentz vector. Now, when you put it this way, well, I just claimed what the transformation is, right? Send E to B, right? And you have to change electric with magnetic. The first two are symmetric. Now, to get these two to work, you have to send B to minus, right? So E to B, B to minus E. And then change all the indices of electric with magnetic. That's the symmetry of Maxwell equations. Good? What that symmetry does is that, how did you define the vector potential? You define the vector potential as something that will basically give you these divergence and curls. If you first do the transformation and then define your vector field, that is the dual vector field. Its corresponding Wilson loop is a Dirac loop. Good? But I'll explain this more. It's just a basic fact about electrodynamics. This is classical physics, by the way. Good? Now, what is this thing? So, by now, you know, why is there Coulomb law? Because putting an electric charge somewhere, you might think that you introduce a local degree of freedom. That's not the local thing. It has to be attached to Wilson line. Right? Put a magnetic monopole. Same thing. It has to be attached to a Dirac line. Right? So when you solve for Coulomb law here, you're basically pretending this is not there, and well, yeah, you're just solving for continuity equation, right? How do you solve for this? What is the solution for a magnetic monopole sitting inside the ball? Right, so I have to draw one higher dimension, so I'm pretending. So I'm going to put a magnetic monopole here, right? The corresponding Dirac line, I'm just going to push it up. Say, oh, sorry, in this picture is going down. What is going on? If you try to solve, so this figure, ignore it for a second, pretend you don't need this line, okay? Try to solve this equation with gradient of B being non-zero. Good? Those are in contradiction. Can you see that? Those two are in contradiction. So what is going on? What's going on is that, well, let's first do the following. Assume, so what's going to happen is that the solution to this, these two are incompatible if you assume that the elect A is single valued. Remember that A to start with was unphysical. A is our attempt to write everything using local language. What is physical are these equations of equations. So if you want to use local language to describe it, using a mu degree of freedom, using a mu is not enough. You should allow for gauge configurations that are topologically non-trivial. They're singular. Okay. So imagine you solve for this on the north pole. So I'm just going to push this down. So on the north side, the upper hemisphere. This is all consistent. You get G over 4 pi r, 1 minus cosine theta over sine theta. This is a solution, simultaneous solution of these two equations with some magnetic monopole put here. Where is the singularity? Theta equal pi. You might have thrown this solution out, but you got to keep it. There is a singularity here. That's a feature of the solution, and that's what the Dirac string is. Why is this a solution? Well, take a n of phi and just take calculate the divergence of it. This is what you obtain. Sorry, the curl of it. This is what you get. It's just a simple calculation. This is what you would expect from a magnetic monopole. Everyone is with me? This is a simple calculation in polar coordinates.
It's transformations of the Lembranch before.
Sorry, here, we're back to first E&M course you took. You don't know anything about relativity. It's just electromagnetism, right? You don't know anything about relativity. What you're trying to do is that you're trying to solve for a magnetic monopole. Somebody comes to you and says, next to electric charge, we have a magnetic charge. Let's just solve for it. You want the magnetic field to come out this way, and you want the magnetic field to be the curl of something. That something will be singular. That's it.
This is all kosher because it's not observable, right? So same
Yeah.
as, yeah.
Well, I mean, why do we remember the logic from to start? Go back to the original logic. E and B are local degrees of freedom. The theory has some non-locality, non-local degrees of freedom, Wilson loops and Dirac loops. A is a made-up invention of humans to describe it locally, right? So if you just took A as you didn't allow for singular solutions, you're going to cover certain aspects of locality, but if you pay attention to these kind of solutions, you're going to get them wrong. We usually don't discuss this in lower level classes because there's no magnetic monopole. there is no law of nature. Well, okay, sorry. Well, we'll get there. We'll talk about this in standard model later on. Good, but this is a simple calculation. Now, is there some meaning to this being in the South Pole? What you could do is you could push the Dirac string to the North Pole this way and solve A of S down here. Right? It's basically the same solution with theta has gone from the singularity has gone from theta pi to theta equals 0. Good. Now, what are we describing? You could describe G cylinder without, because the whole point of A is to describe it without the string, right? You could describe it in the following way. You could describe it with some sort of configuration that has a singularity here, only there, or you could describe it as something that has singularity only over there. But let's play the following game. First, take this solution that's singular down here, cut it, and keep the smooth part of it on the upper half. That's AN solution. Then take the solution that is singularity here, take the smooth part of it A south. Because you want to get rid of the Dirac string, you have to solve AN and AS, right? But what happens is the following. AN is AS plus 1 over sine theta del phi of omega. And omega is G phi over 2 pi. G is the magnetic monopole. So it's not single valued. As you come down here, so the solution you find, the solution you find here, if you go around by 2 pi, it will get shifted by this, Good. So you could get rid of the Dirac line at the cost of introducing these. The Dirac line was some sort of like singularity near A, at the cost of allowing for non-single valued field configurations. I know that I'm going over this quickly, but these are simple electromagnetism calculations. It's not even dynamics. It's just everything is static. Good. It's just Carroll and vector, whatever they call it. What algebra? Vector algebra, vector calculus. Now, there is something profound going on here. Do I want to say this? No, I want to skip this. This is a little bit too advanced. All right. There's something crazy going on here. The electric charge and the magnetic charge cannot be whatever you want. They have to be related. This is the so-called Dirac quantization rule. There is no quantumness here. It's just the consistency of the equation. There is quantumness, but I'm not talking about H bar yet. Well, actually, let me go over this. I have to go talk about H bar actually. We talked about this, right? A gauge transformation. We talked about what was the physics of Wilson loop? The physics of the Wilson loop was that you send two particles, there's some magnetic field going through the board, right? Say particle this way, there will be a phase difference, right? That's the physics of the Wilson loop. And that's okay because the physics, like e to the power of I, e omega over h bar is the transformation of the wave function under such a loop, right? You go around, it will transform by this much. And this is a gauge. This is pure gauge. Sorry, everybody's following me or am I going too quick? At any point here, the electric and magnetic fields are 0. You might think you could choose A mu to be 0 everywhere. You cannot, because the theory is non-local. There is magnetic field going through this. So A mu, you could locally trivialize at every point, but the integral around this is a physical observable. And it acts physically on the wave functions this way. Right? This is the whole lot of everything that we discussed. We talked about this, right? There's a U1 bundle. Good. Now, what we're gonna see is that this requirement will imply a quantization condition. The electric charge times the magnetic monopole charge, the fundamental units of them have to be 2 pi n h bar. How do I get that? Well, replace this magnetic field by some sort of magnetic charge sitting here, monopole sitting here. Now there are consistency relations that I'm gonna solve in the next slide. What is the consist? This is precisely the next slide. So here's your Wilson loop. This is the magnetic charge. Consider magnetic monopole, G here, and then we're gonna go around this. This will cause some B here. That will give some non-trivial Wilson loop here. So the question is, you have a charged particle here, you go around the loop, how much does the phase change? Good. So what is the answer? Integral of A dx. That is by whatever theorem, I forget the name of it. You write this as a surface integral. That is integral of dsB. So this is the solid angle, G over 4 pi. That's your answer. Do you see a puzzle? What's wrong with this argument? There's nothing wrong with it, but there's a puzzle. You should be perplexed by this. The physical question I'm asking is this. I put a magnetic monopole here. I have an electric charge here. I go around the loop. How much does the phase of the wave function of the electron change? It changes by this much, right? Omega g over 4 pi. Well, this is the phase it requires. Alpha is omega g over 4 pi, and it changes by I alpha e over h bar. Do you see the puzzle? Who said this is the surface and not this? What do you get if you do it the other way? Instead of solid angle omega, you get 4 pi minus omega, and you pick up a minus sign because B was sticking out, B is now the other direction. Good? This is all nonsense unless these two phases match. That requires that E times G is 2 pi and H bar. End of the story. This is called the Dirac quantization rule. Sometimes discussed in Sakurai as well. This is like, because it doesn't require relativity or anything. It's just like a simple consequence of it. Why haven't we observed this? G is 0 so far, right? So there's no condition so far. But if G is non-zero, if there is one day there's a magnetic monopole discovered in the universe, this will immediately apply. You know the size of it. It has to be 2 pi h bar over E. Right? Times an integer. So at least it's that. So the charge quantization tells you the smallest charges you could have. You could have multiple of them, of course, but this tells you about the smallest magnetic monopole charge you could have. If you don't want a charge quantization, the other way out is to say magnetic monopoles are disallowed. Okay? That will be a way around. In general, in electrodynamics, a particle, so we've talked about a particle that's charged on the electric field, a particle that's charged on the magnetic field. Well, sorry, charge something that a particle that solves this same particle can solve this. Electron is something that has this 1 or whatever is the appropriate thing, 0. A magnetic monopole has something here, 0 here. In general, the theory allows for charges that have both, they're called dions. But if E, okay, so a general particle satisfies E and G. This is the labels. Here's a homework problem for you guys. Take 2 such particles, play the game we just played. Put in the center a dion with E1, G1. Take a dion with E2, G2, and go around the loop. What is the quantization condition you find? You find the following quantization condition. E1, G2 minus E2, G1 has to be 2 pi n h bar.
Same thing, somewhere.
Yeah, same exercise. Exactly same exercise. You find the following quantization condition. So it also constrains the relative charges. All right, questions. I know that I'm going through this really, really fast. But this is, I trust you could reproduce these because the calculations are really like college level physics. Good. So now what is a Dirac loop? It's the dual, it's a twist operator, if you wish, right? The dual to, well, take a region in electrodynamics that has non-trivial pi 1. Here's a Wilson line. This Wilson line will tell you about the failure of duality for Higgs duality for the complementary region. What is the object, the twist, the operator that tells you about the failure of duality for this region? It's some integral of something around this with the dual field. That's called a Tooth loop or a Dirac loop. Tooth loop whenever it's non-abelian, right? The original version of it is because QED, NM is abelian. The story is more complicated when it's non-abelian. All right. Okay. And then there are charge quantization conditions. We talked about that. All right. So let's go back to electrodynamic Maxwell equations. What was the action we wrote? We wrote F mu nu. What is that? That's E squared plus B squared. Right? E was F0I, EI was F0I, and Fij is minus epsilon ijk bk. Right? That's just saying that the F mu nu is a covariant way of packaging electric field. Magnetic field. Oh, thank you. Oh, ooh, I'm gonna get these wrong. B. Bees, bunch of bees. This. Okay. What is the canonical dimension of F mu nu? What is the dimension counting dimension of F mu nu? F mu nu squared is 4. Yes. So anything that has more F's is going to be irrelevant. But we can still add a term which is second order in F. using what's called the theta term. Can you guess what that term is? What can I add to this that will correspond to something that's second order enough? E dot B. I can add to this E dot B. Can you write E dot B in terms of F? Yes. You introduce the Hodge dual to this F mu nu this way. These are four, these indices are Lorentz invariant, right? One's covariant. So star of F mu nu is the same as F mu nu with E going to B, B going to minus E. All right. So if you put star of F mu nu with some coefficient here that I put a theta, I put E squared over 4 pi squared and some theta here. This is what the what does this term do? This term changes sign under this transformation. So it breaks the symmetry. Right? This duality symmetry is broken by this term. The fact that this term is not around is because Maxwell equations have this symmetry. So theta parameter, first of all, this theta parameter is dimensionless. And if it's 0, we have this symmetry. But if you look at this action, this is a total derivative. This is a total derivative. We could write it this way. The term is topological. It does not change the equations of motion. So you could add it without any issues. We're not going to discuss this. It has consequences for quantum mechanics, but not classical physics. Quantum mechanically could distinguish whether this term is 0 or not. Classically, we cannot, because Maxwell equations remain the same. This term is topological. If you want an exercise, take this action and derive the equations of motion from it. Good. So yeah, I went through this way too fast. But in summary, what did we talk about? So we use a language that's purely local to unify gauge theory with gauge symmetries. Sorry, theories with gauge charges, theories with global charges, and theories with generalized symmetries, arc form charges. Okay, zero form symmetry became global symmetry. One form symmetry became gauge theory. So I told you a long time ago, gauge theories should not be called gauge symmetries because there's no actual symmetry. But now I'm calling them one form symmetries. There's no this. When people call this gauge symmetry, they were thinking of a local transformation. There is a symmetry, but it's non-local, right? There's a symmetry and it's non-local. But R form, and then the R form version of it is all about the failure of duality for various topological and non-trivial regions, right? Every time you have one of these non-local operators, it comes with this dual corresponding to the causal complementary region. Now, as you probably can guess from electrodynamics, there will be quantization rules. So all the structure will generalize. Why did I jump to 4 dimensions? Okay. So what is F? F is dA. Right? This is just saying that I put together the 2 equations, right? I define for you F tilde. What do they call it? Oh, I didn't call it anything. Star. This is also a 2 form. This is D of A tilde. Good. Now, if you know a little bit about Hodge duality, if this is a P form, this is a D minus P form. And from this equation, you'll learn that A tilde is a D minus P minus 1 form. Good. A P form could be integrated over a surface that's a D minus 1 surface. Sorry, what am I saying? Anyway, so in electrodynamics, this is a 1 form, this is a 2 form. In 4 dimensions, so this is a 2 form. In 4 dimensions, you're in this sweet spot, which is also a 2 form. Therefore, A tilde is also 1 form, so it's still a loop operator. But in different dimensions, the object, the dual object you find is different, so you have to integrate a different surface. So these would be non-local operators of various dimensions. All right. We'll come back to this symmetry. The existence or absence there of theta parameter. It has important consequences for electrodynamics, or basically for non-abelian gauge theories. Non-abelian gauge theory aspect of it is really super advanced. It's research material. I do recommend a set of, if there are courses on there are whole courses on quantum gauge theories, and a huge part of those courses, like for example, David Tong taught such a course at Cambridge. You can find lecture notes, is about examples of this theta term and the physics of it quantum mechanically. I covered this in the course I taught a couple of years ago. All right, any questions? This is the end of this chapter. We're gonna let go of this stuff, go back to Lagrangians. All right, we're gonna go back to Lagrangians and discuss spontaneous symmetry breaking. And then the last topic of the course will be, we'll actually also discuss anomalies and then standard particle physics. That's the remainder of the course. Right? But this was the only detour I did because I think in a few years it will be textbook material.
The loops are have been observed.
Sorry?
The loops.
Tooth loops. No.
Not in the same sense as.
So in electrodynamics, as we see it, there's no magnetic monopole. It has not been observed, right? Therefore,
that's the only way we can observe.
Remember here, I said there are 2 ways out of this.
Yeah.
The other way is that there's no monopole.
And the other is
Non-abelian gauge theory story is very complicated. Yeah, let's look at that. That's pretty advanced. When you have a non-abelian gauge theory, yeah. Again, quantum gauge theory could be a whole course that deserves to be QFT3. All right, any other questions? I just wanted you guys to have seen this a little bit because it will help in your research. For example, I don't know if last time I taught this, I covered this. I'm just going to mention it. So there is something called axion electrodynamics. It's important in astrophysics. The theory of topological insulators is all about this theta term as well. Okay, there's Hall conductivity that could be explained using this, and blah, 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 quantum Hall effect, all of this. So this physics is, of course, if we are making a basic statement about electrodynamics, is going to be profound. It's going to have applications everywhere, condensed matter, in astrophysics, everywhere, right? And it does. That's why it's in Sakurai. Yeah.
So far, we haven't seen anything mathematically that rules out monopoles, magnetic monopoles. But are there things we haven't seen that do rule them out, or there's just nothing so far that rules them out?
It's a simple observation that we have not seen them. Nothing forbids them. Nothing forbids them.
Then is it like a mystery why we don't see them? I guess.
So when we get to standard model particle physics, like, so here, in standard model, you've heard about the parameters, right? So you write down mu nu f mu nu 1/2g, right? 4g, whatever. And then you will include this theta term, g something, I think g squared, da da da, in the middle of f with star f. This is the theta term. This has been, you do experiments and read it off. This, we do experiments and read it off, and there are bounds on how large it can be. So there are bounds on how small this is, I guess, at the moment. But the experiments continue to circulate. I'll describe the physics of that, what it does. All right. Any other questions? It is a parameter standard model, if you wish, generalized standard model. It's something that we look for in experiments. Any other questions? Not, thanks so much, guys. As I said, the rest of the course is going to be about